Hello students, this is part 3 of a 3-part series on inverse trigonometry. Now like for the sine, cosine, and tangent, the cosecant, secant, and cotangent functions all, when graphed in their entirety, fail the horizontal line tests. They are not one-to-one functions. This is the graph of sine of x, and cosecant is the reciprocal of this graph, so wherever this graph has an x-intercept, the cosecant graph will have a vertical asymptote, and here is the cosecant graph. It also fails the horizontal line test. Here's a horizontal line that intersects the cosecant graph in multiple places. However, if you crop the cosecant graph and keep only the portion of it between x equals negative pi halves and x equals pi halves, we will have a one-to-one function. So limit our domain to these x values, and these are angles. Notice we have to exclude 0 because there's a vertical asymptote when x is 0. But we do retain the angles negative pi halves and pi halves because the cosecant is defined. At negative pi halves, the cosecant is negative 1. And at pi halves, the cosecant is positive 1. At negative pi fourths, that is coterminal with this angle at 7 pi fourths. And the cosecant is the reciprocal of sine. Sine is the second coordinate. So we do the reciprocal of that and get negative 2 over radical 2, which when you rationalize and simplify becomes negative radical 2. At the angle 0, that's this position of the unit circle, the sine is 0 and we cannot reciprocate 0, which is why we have our vertical asymptote when x is 0. And then at angle 0.8 radians, use a calculator, and we get about 1.394. Now keep in mind that all of these outputs are ratios. And for the cosecant, that ratio would be the reciprocal of sine. Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. And we'll interpret these outputs as y-coordinates, and the inputs as x-coordinates, which are angles in this limited window. And these are the inputs and outputs of the function f, as defined over here. Our inverse function will do the reverse. It's the ratios that will be the inputs, and the angles that will be the outputs. So the inverse function of f will be the inverse of the cosecant, so we can write that as CSC with a negative 1 power, and we say inverse cosecant, or you can write Arccosecant of x. Again, all of these input variables are dummy variables, meaning they can really be any letter as long as you're consistent. But since our inputs correspond to ratios and we call them y in this context, I'll use y as the input variable again. And the domain of the inverse function will be these ratios, and the range will be the outputs, and the outputs are these angles. Notice that the range outputs angles that are from negative pi halves to 0, so here in the fourth quadrant, or from 0 to pi halves, so here in the first quadrant. So just like inverse sine, the outputs are in the fourth or first quadrants, and if in the fourth quadrant, we must use a negative angle to get there. Notice that for the cosecant function, it's impossible to get a ratio that's in between negative 1 and 1. So any horizontal line that's in this window here from y equals negative 1 to y equals 1, there's no angle at which the cosecant will be these values. That's why our ratios are missing entries between negative 1 and 1. Hence, the domain of the inverse cosecant function has that same limitation. Okay, let's evaluate the inverse cosecant function at a few different inputs. Looking at this first one right here, the inverse cosecant of 2 over radical 3. Now, sometimes a unit circle will be useful when doing this, and sometimes it won't be, and we'll have to use a calculator. So when I say the inverse cosecant of 2 over radical 3, this means I'm trying to find an angle that's in the fourth or first quadrant at which the cosecant will be 2 over radical 3. And the cosecant of an angle is the reciprocal of the sine. So if the cosecant of the angle I'm looking for is 2 over radical 3, then the sine of that angle would be radical 3 over 2. So then you scan these quadrants, and you look for a point where the sine will be radical 3 over 2. And it should happen only once, and it happens at this angle right here because the sine is radical 3 over 2. Therefore, the cosecant of this angle will be 2 over radical 3. So the angle I'm after is this pi thirds, or 60 degrees. Now the arccosecant of negative 2, again, this is just inverse cosecant of negative 2. So we're trying to find an angle at which cosecant is negative 2. Well, at that angle, sine would be negative 1/2. So looking across the fourth and first quadrants, looking for an angle at which the sine is negative 1/2 should occur only once. It's right here. But these angles are positive and too large. They're not inside our range. Do not say 330 degrees is an answer here because that does not satisfy our range over here. So if we're in the fourth quadrant, we have to use a negative angle to get there. So this would be negative pi 6 radians, which is negative 30 degrees. And then finally, the inverse cosecant of 4. is an angle at which cosecant is 4, which means at that angle sine would be 1/4, but you will not see 1/4 in any of those positions. In fact, this vertical height here is 1/2, because that's the second coordinate. Half of that is 1/4. So somewhere in this area is where you would expect to have a second coordinate of 1/4. So this is the angle we're looking for, and we'll use technology to find it. Okay, so type in arccosecant of 4. Click the wrench to see that you are in radian mode. So our answer is about 0.253 radians, rounded to the nearest thousandth. Or in degrees, it's about 14.5 degrees, rounded to the nearest tenth. So I'll cross out this equal sign and say approximately 0.253 radians, or 14.5 degrees. Notice that's a sensible answer given we expected an angle somewhere around here. Now if I'd asked you to find the inverse cosecant of 1/2, if you type this into your calculator, you'll get a does not exist, or an undefined. There is no angle at which the cosecant can be 1/2, because 1/2 is precisely in this missing portion of our number line between -1 and 1. And in the graph of cosecant, an output of y equals 1/2 is at this height, and you can see it does not intersect the graph. Okay, next slide. Recall the graph of secant by first looking at a graph of cosine, seen here in red, and wherever cosine intersects the x-axis is where secant will have a vertical asymptote, and then secant is the reciprocal of the cosine, giving us this function here. Also, it fails the horizontal line test. Here are several points of intersection with a horizontal line. But if we crop the graph in the following way by keeping angles only between 0 and pi, we get this portion of the secant curve, which is a 1-to-1 function because it passes the horizontal line test. So this function f will input an x-coordinate, which will be an angle, somewhere between 0 and pi, but excluding pi halves because that's where the asymptote is. The secant of pi halves does not exist. And we'll output a ratio, and for secant, that ratio is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, and we'll consider this ratio a y-coordinate, which is the output. So secant of pi 6, let's use the unit circle to help us with that. Here's pi 6. The cosine is the first coordinate, rad 3 over 2. So the secant of this angle is its reciprocal, 2 over rad 3, which if you rationalize is equal to 2 rad 3 over 3. Now secant of pi halves points up. The first coordinate is 0, and 0 you cannot reciprocate, and we get dne, because at angle pi halves, we have our vertical asymptote, and there's no output. Venturing into the second quadrant, this portion of our angles, 2 pi thirds is this location. The first coordinate is -1/2. The secant is the reciprocal of that, so -2. 2.9 radians is a little bit less than 3 radians. Pi radians points on the left side of the circle, so I expect 2.9 radians to be an angle somewhere around here. But 2.9 radians is not an angle on the unit circle, so I'll use a calculator and type in secant 2.9. Make sure you are in radian mode, and you get approximately -1.030. And then finally at pi points on the left side of the unit circle. First coordinate is -1, and the reciprocal of -1 is still -1. This corresponds to this point over here in our graph at pi -1. And this is the largest angle that we would want to plug in to this cropped version of secant of x. So this cropped version of secant of x has an inverse. That inverse is going to treat the ratios as inputs and the angles as outputs. The notation for the inverse function is either secant to the -1 of the input variable, or you can say arcsecant of the input variable. And again, the letter I use for the input variable can really be any letter, but since we used y for the ratios, let's use y's as our inputs of the inverse. And the domain of this inverse function will be precisely these ratios, again, with a gap between -1 and 1. This is the same domain as the inverse cosecant function, but the range will be very different. The range will be angles in the first or second quadrants, whereas for arccosecant, it was fourth or first quadrant. This corresponds to angles that sweep out the first quadrant or the second quadrant. Of course, pi halves would not be possible, because the secant is undefined at pi halves. Okay, let's evaluate a few inverse secant functions at different inputs. Looking at this first one, once again, for some of these, the unit circle may be useful. In others, we might just need a calculator. So I'm trying to find an angle that's in the first or second quadrant at which the secant is -2 over rad 3, which means the cosine will be the reciprocal of this number, -rad 3 over 2. So looking at all the first coordinates across the first and second quadrants, look for a -rad 3 over 2, which happens right here for this angle. This is an angle that's in the second quadrant. It's in this interval from pi halves to pi. Therefore, it is an acceptable answer. 5 pi 6 radians, or 150 degrees. Look at the next one. Arcsecant of radical 2. So we're trying to find an angle in the first or second quadrant at which the secant is radical 2, which means the cosine will be the reciprocal of radical 2. And keep in mind that the reciprocal of radical 2 is 1 over radical 2, which you will not see as any of these first coordinates in the first and second quadrant. But you must be careful because 1 over rad 2, if you rationalize it, will be rad 2 over 2. And that I see right here as the first coordinate. So this is the angle at which the cosine is rad 2 over 2, which means the secant is 2 over rad 2, which simplifies to simply rad 2. Therefore, this is the angle that we're looking for, so pi force radians or 45 degrees. Now the arcsecant of 0.7, the reciprocal of 0.7 is 10/7. You're not going to see that anywhere using the unit circle, so let's reach for a calculator. And you can type in arcsecant 0.7 or secant to the -1 of 0.7, and notice we get undefined, while in radian mode and also in degree mode, it doesn't matter. And that is because 0.7 is not in our domain, because it's in this missing portion of our domain between -1 and 1. 0.7 is not a possible ratio when doing the secant function. Okay, let's move on to the next slide. This is a graph of the cotangent function. You can see it fails the horizontal line test. Here's a horizontal line intersecting multiple times. But if we keep just the portion between x equals 0 and x equals pi, then we do get a 1-to-1 function that covers the entire range. So limit our angles to 0 to pi, but exclusive of 0 and pi because the cotangent is undefined at both 0 and pi. That's where we have asymptotes. So this function f will input angles between 0 and pi and output ratios. And the cotangent is the reciprocal of tangent. Tangent is opposite over adjacent. So cotangent specifically gives us adjacent over opposite. And these outputs are y-coordinates in our graph here. The cotangent of pi 6 is here. Cotangent is cosine over sine. So we would do the first coordinate divided by the second coordinate. So rad 3 over 2 divided by 1/2. This simplifies to rad 3. Pi force, first coordinate divided by second coordinate. Well, at this angle, sine and cosine are equal, so we get a cotangent of 1. That corresponds to this point over here, a very important point with cotangent. It's the angle at which the output is 1. At pi halves, that's pointing up. First coordinate divided by second coordinate, we get 0 over 1, which is just 0, giving us this x-intercept. Now 2 radians, the unit circle will not be helpful with this. 2 radians is somewhere in the second quadrant. 1 radius length is about there, 2 radius lengths, 3 radius lengths, and pi radius lengths get us halfway around the circle. But 2 radians would point somewhere into the second quadrant. And using a calculator and making sure you are in radian mode, we get about -0.458. Now 5 pi 6 is on the unit circle, first coordinate divided by second coordinate, and that gives us negative rad 3. Now this portion of the cotangent graph is 1-to-1, so it has an inverse. The inputs will be the ratios, and the outputs will be these angles between 0 and pi. That's first and second quadrant, top half of the unit circle. So this inverse function, we'll use y as the input variable, since we've been using y as the ratio, and we input the ratio. We can write cotangent to the -1 of y, or arccotangent of y. The domain will be these ratios from -infinity to infinity, so there are no limitations on what the input of the arccotangent can be, and the range will be these angles between 0 and pi exclusive. Let's evaluate the arccotangent function at a few different inputs. Looking at this first one, we're trying to find an angle at which the cotangent is -1 over rad 3. Well, it's going to have to be a second quadrant angle, because in the first quadrant, cotangent is positive. In fact, all trig functions are positive in the first quadrant. And since cotangent is cosine over sine, we need to find an angle at which the first coordinate divided by the second coordinate will be -1 over rad 3. That actually occurs at this angle right here. First coordinate is -1/2, second coordinate is rad 3 over 2. And when you simplify that, you do get -1 over rad 3. So the cotangent at that angle is -1 over rad 3. Therefore, that angle is the angle that we are trying to identify. And it is in the second quadrant. In other words, it's between 0 and pi. So this inverse cotangent will give us 2/3 of pi radians, or 120 degrees. This next one, arccotangent of rad 3, we are trying to find the angle in the first or second quadrant at which the cotangent will be rad 3. Well, this will have to be in the first quadrant. And in fact, we already have that in our table up here. At angle pi 6 is when cotangent will be rad 3. So the arccotangent of rad 3 is this angle pi 6, which in degrees is 30 degrees. Now arccotangent of 50, the unit circle will not be helpful with this one. So type in arccotangent 50 or cotangent to the -1 of 50, make sure you're in radian mode, and we get about 0.01999, which rounds to about 0.20, when rounding to 3 decimal places. And in degrees, that corresponds to about 1.1 degrees when rounding to the nearest tenth. So we'll say about 0.020 radians, which is about 1.1 degrees. Notice our graph here only shows going up to height 4, but imagine we needed to get to a height of 50. That'd be very far up there, which is why we're getting such a small x-coordinate here needed to get to that height, where the x-coordinate is the angle. That's why arccotangent of 50 is so small. All right, next slide. Now that we've investigated the inverse trig functions for all 6 trig functions, we can do a summary of their ranges. 3 of the inverse trig functions had ranges in the 4th or 1st quadrants. They were the arcsine, the arctangent, and the arccosecant. And specifically, the ranges were arcsine had to be an angle somewhere between negative pi halves and pi halves inclusive. Arctangent's range was negative pi halves to pi halves exclusive, because the tangent's undefined at negative pi halves and pi halves. And the arccosecant was like the arcsine, except we had to exclude 0, because the cosecant is undefined at angle 0. Now the other 3 inverse trig functions had ranges that were either in the 1st quadrant or the 2nd quadrant. Those were the arccosine of y, arccotangent of y, and arcsecant of y. And specifically their ranges were arccosine of y had to be somewhere between 0 and pi inclusive, arccotangent of y had to be somewhere between 0 and pi exclusive, because cotangent's undefined at 0 and pi, and arcsecant was similar to arccosine, except we had to remove pi halves, because the secant is undefined at pi halves. Now for all of these inverse trig functions, if y is positive, the angle you're looking for will be in the 1st quadrant. But when the input y was negative, then for these 3 inverse trig functions, we're looking for a 4th quadrant angle using a negative angle to get there. But for these 3 inverse trig functions, we are looking for a positive angle that's in the 2nd quadrant. All right, next slide. Use the unit circle to find the following values. Confirm your answers with technology. So these problems involve finding the inverse trig of a trig expression. We're going to work inside the parentheses in each case first. So let's first find the sine of 4 pi thirds. 4 pi thirds is an angle in our unit circle. It's here in the 3rd quadrant, and the sine is the 2nd coordinate. So I'm going to replace sine of 4 pi thirds with its result, which is the ratio negative rad 3 over 2. And now as a second step, I'm looking for the arcsine of negative rad 3 over 2. So I'm looking for an angle at which the sine is negative rad 3 over 2. And you might say, well, just keep the same angle, 4 pi thirds. However, the arcsine must output angles in the 4th or 1st quadrants. But when trying to find the inverse sine of a negative ratio, then we're really looking for an answer that's in the 4th quadrant. So looking at the 4th quadrant, scan the 2nd coordinates looking for negative rad 3 over 2, which is right here. However, we must find a coterminal angle that's negative. So instead of using 300 degrees, which wraps counterclockwise mostly around the circle, describe this location using a negative angle, negative 60 degrees, or negative pi thirds radians. All right, the next one, find the sine of 4 pi thirds. We've already done that. 2nd coordinate is negative rad 3 over 2. And now as a second step, we want to find the arccosine of this ratio. Arccosine will produce an angle that's either in the 1st quadrant or 2nd quadrant. But since we're doing the arccosine of a negative ratio, that means we want to look in the 2nd quadrant. And since the cosine is the 1st coordinate, try to find the angle at which the 1st coordinate is negative rad 3 over 2. That happens at this angle. And this angle is between 0 and pi, so we don't need to tweak it to a coterminal angle. And we get 5 pi 6 radians, or 150 degrees. All right, the next one, cotangent of 3 pi fourths. 3 pi fourths is this angle, and we do cotangent by doing cosine over sine, so 1st coordinate divided by 2nd coordinate. So the cosine is negative rad 2 over 2, and the sine is rad 2 over 2, so we get a negative 1 ratio. So inside these parentheses is simply negative 1, and now our goal becomes to find the arctangent of negative 1. Arctangent is an angle somewhere in the 4th quadrant or 1st quadrant, but since we're doing the arctangent of a negative ratio, it's going to have to be in the 4th quadrant. And we want to find the angle at which the tangent is negative 1. Well, tangent is sine divided by cosine, so it's 2nd coordinate divided by 1st coordinate in the unit circle. And we get the tangent to be negative 1 at this angle, because the 2nd coordinate is negative rad 2 over 2, the 1st coordinate is rad 2 over 2, divide those, you get negative 1. However, 7 pi fourths is too large of an angle to use. You must use a negative coterminal angle, so negative pi fourths. or negative 45 degrees. Next one is secant 4 pi thirds. 4 pi thirds is here. Secant is the reciprocal of cosine. Cosine is negative 1/2. So we get 1 over negative 1/2. That simplifies to negative 2. So inside these parentheses is simply negative 2. So now our goal is to find the arccosecant of negative 2. The arccosecant will be an angle in the fourth quadrant or the first quadrant. But because we're doing arccosecant of a negative angle, we must be looking in the fourth quadrant. And we're trying to find an angle at which the cosecant is minus 2. The cosecant is a reciprocal of sine. Therefore, the sine at this angle would be negative 1/2. And the sine is the second coordinate, so I see that right here. And we need to use a negative angle to get to this location. Negative pi 6 radians, which is negative 30 degrees. All right, next one, let's do tangent of 3 pi fourths. 3 pi fourths is here. Tangent is sine over cosine, so it'll be second coordinate divided by first coordinate. So the sine at this angle is rad 2 over 2, and the cosine is negative rad 2 over 2, and we get negative 1 here. Notice this is the same angle that we did cotangent at, which is also negative 1. Cotangent and tangent are reciprocals of each other, so if cotangent is minus 1 at this angle, the reciprocal of that would be tangent, and the reciprocal of negative 1 is still negative 1. So having done the inside of these parentheses, we got a minus 1 ratio. And now we want to do inverse secant in the first or second quadrants. But since we're doing the inverse secant of a negative, that means we must be looking in the second quadrant, or even potentially at the left end of the unit circle, which is actually where this is going to occur. Because at angle pi, the cosine is negative 1, therefore the secant is the reciprocal of that, which is still negative 1. Therefore, pi radians is the angle at which secant is negative 1, and that, of course, is 180 degrees. And finally, let's do this last one. The inside of the parentheses is the tangent of negative pi thirds. So we have a negative angle here. Negative pi thirds takes us to an angle that's coterminal with 300 degrees or 5 pi thirds. And the tangent will be the sine divided by the cosine, so second coordinate divided by first coordinate, which simplifies to negative rad 3. So the inside of our parentheses is negative radical 3, and now we are trying to find the inverse cotangent of this ratio. Well, inverse cotangent would be an angle somewhere in the first quadrant or second quadrant, but because we are doing the inverse cotangent of a negative, we expect the answer to be in the second quadrant. And the cotangent is cosine divided by sine. So we're trying to find an angle where the first coordinate divided by the second coordinate will be negative rad 3. That will occur at this angle here. Because the first coordinate is negative rad 3 over 2, the second coordinate is 1/2. So when you do first coordinate divided by second coordinate, you will get negative rad 3. So this is the angle we're after, 5 pi 6 radians, or 150 degrees. Now let's use technology just to check this last one. Make sure you're in radian mode. The tangent of negative pi thirds in decimal form is about negative 1.732, which is really the negative square root of 3. So I've typed both in so that you can see that they are the same. Let's call this first one A, because now I want to do the inverse cotangent of this. So instead of typing in tangent negative pi thirds, I can just put A, and we get this value, which we just claimed is 5 pi 6, which when I type in 5 pi 6, you can see we get the same decimal representation. So this confirms our work that the inverse cotangent of the tangent of negative pi thirds will be 5 pi 6. If you switch all this work to degrees, you're going to see some things go wrong here. And that's because the first line is assuming negative pi thirds is a degree measurement. So you would have to change this input to negative 60 degrees. And now you can see that the tangent of negative pi thirds radians, or in other words, the tangent of negative 60 degrees, is the same thing as negative square root of 3. And the inverse cotangent of that is 150, meaning 150 degrees. Okay, let's go on to the next page. Find the following values without technology, but confirm your answers using technology. So we're doing some more compositions of trig with inverse trig. In this case, inside the parentheses is an inverse trig function. And then we'll do a trig function of that. Now, inverse trig outputs angles. So this inverse sine of 5, 6 is some sort of angle. Notice that the 5, 6, the ratio, is positive. So I know that the angle I'm looking for is a first quadrant angle. And it's an angle alpha at which the sine will be 5, 6, which means I can make a reference triangle. So you have a right triangle, put our acute angle in the first quadrant, alpha in one corner, and we know the sine is opposite over hypotenuse, so let's say the opposite is 5 and the hypotenuse is 6. Use the Pythagorean theorem to get the other side, so we'll square the hypotenuse, which is 36, remove the square of the leg, which is 25, 36 minus 25 is 11, and then take the square root of that. So now we are trying to find the cosine of this same angle. So using our reference triangle, we can say that the cosine of this angle must be the adjacent divided by the hypotenuse. And we get rad 11 over 6. Okay, for this next one, the inside of the parentheses is also an inverse trig function. This is some sort of angle, I'll call it beta this time. But notice that because we're trying to find the inverse tangent of a negative, then we're not going to be in the first quadrant. And for inverse tangent, the possible quadrants are fourth or first quadrants. So this must be a fourth quadrant angle beta, and a negative angle at that to get to the fourth quadrant. We also know that the tangent of beta must be this ratio of negative 7/3. Let's make a reference triangle and position it in the fourth quadrant. The reference triangle does not need to be to scale. It's just a tool. It's a right angle. And our angle beta is this negative angle that takes us into the fourth quadrant. And we want the tangent, which is opposite over adjacent, to be negative 7/3. So in the fourth quadrant, it's the vertical leg that would need to be negative. So that's negative 7. And the horizontal leg would be positive 3. Pythagorean theorem will give us the hypotenuse, square 3, square negative 7, so we get 9 and 49. Add together, gives us 58, and take the radical. That would be the hypotenuse. Now we can use our reference triangle to say, well, what is the secant of this same angle beta? Well, secant is the reciprocal of cosine, so it's going to be hypotenuse divided by adjacent. So we get rad 58 over 3. So this is a good approach for when you're doing a regular trig function of an inverse trig function. Over here, we have inverse trig of regular trig. That's similar to what we did all on this last page, was inverse trig of regular trig. However, on this last page, I was careful to choose angles and trig functions for which the unit circle would be entirely useful to resolve the task. Down here, we're going to be doing the same kinds of questions, but for which the unit circle will not be useful. Focusing on inside the parentheses, we want to do the cosine of 7 pi fifth, and we're going to be doing this without technology. We know that half a rotation around the circle is pi, so break this into fifths. And this can be tricky to do in your first attempt, but you can adjust until you feel that roughly we've done 1, 2, 3, 4, 5 equal rotations to go pi. Of course, we want to now do 7 pi fifths. So now we have 1, 2, 3, 4, 5, 6, 7 pi fifths. So if you did make a little right triangle here, the cosine would be some value. The two coordinates would be a negative, and then we'd have some positive hypotenuse. So looking at this image, without knowing what these values actually are, the cosine would be negative a over c. Now whatever these values are, we now want to just do the inverse cosine of this. However, inverse cosine will only give me an answer that's in the first or second quadrant. I cannot use a third or fourth quadrant angle. Furthermore, because this ratio would certainly be a negative ratio, since cosine is negative in the third quadrant, that the inverse cosine would have to give me an angle somewhere in the second quadrant. The cosine of this angle I'm looking for to be negative a over c. Well, all I have to do is draw the same reference triangle that has a negative a over c adjacent over hypotenuse. Of course, the other leg would be now positive b instead of negative b. So here's a reference triangle that's in the second quadrant, and the cosine is negative a over c still. And the angle that takes us to this position is only 3 pi fifths. This is the angle that this inverse cosine will produce. Remember, it has to be somewhere between 0 and pi, first or second quadrant. This next one is similar. We have tangent of 7 pi fifths. So again, I do 7 pi fifths of an angle. I imagine there being some sort of reference triangle. The legs will label negative a and negative b. Hypotenuse will label c. So given this labeling, the tangent of 7 pi fifths will be opposite over adjacent. The opposite is negative b, and the adjacent is negative a. We're both negative, so this will simplify to a positive number. Now we want to do the inverse tangent of this positive b over a. Well, because this is positive, I know that the inverse tangent of this positive angle should be in quadrant 1. All 6 inverse trig functions, when the argument is positive, the angle that you're looking for is a quadrant 1 angle. So I need to find the angle that will produce a similar triangle, but that's in the first quadrant. And that's going to be this green triangle. Same dimensions, but positive values. So positive a will be the adjacent, positive b will be the opposite, and c will still be the hypotenuse. And this angle here is 2 pi fifths. This is the angle we are looking for. Let's confirm this one with technology, and then this one with technology. Here's the arcsine of 5/6, and I have it set in degrees. And let's call this angle A. Now let's find the cosine of this angle. And we get this result. And we claim the answer was radical 11 over 6, which gives us the same decimal. So this confirms that the cosine of the arcsine of 5/6 is radical 11 over 6. Confirming our result here. Now confirming this next one, the cosine of 7 pi fifths This time let's make sure we're in radian mode because 7 pi fifths is a radian measure. And we get this ratio. Let's call this ratio A. Now we want to do the inverse cosine of this ratio. And we're still in radian mode, so this is a radian answer. And we claim that our answer is 3 pi fifths. And sure enough, we get the same decimal representation. So this confirms that the arc cosine of the cosine of 7 pi fifths is 3 pi fifths, confirming our conclusion up here. I encourage you to verify the other two as well. Okay, next page. Creating a general reference triangle. Suppose that theta equals arccotangent of u and is in the first quadrant. Find expressions that represent the values of all 6 trig functions at that angle. Well, I've broken this down into 3 steps to follow. Step 1, express the inverse trig statement as a regular trig statement. So theta is the arccotangent of u. So u is a ratio and theta is an angle. Therefore, the cotangent of that angle theta will be equal to that ratio u. And cotangent is adjacent over opposite. So think of this u as being over a 1. This allows us to do step 2, which is use the trig statement to draw a reference triangle and use the Pythagorean theorem to find the missing side of the triangle. So we draw a reference triangle. Remember, we are assuming that theta is first quadrant. Furthermore, we want the cotangent of this angle to be u, and we're thinking of u as being u over 1, where u is the adjacent and the opposite is 1. Pythagorean theorem can let me find the last side. If I call it c for a moment, so we know that u squared plus 1 squared would have to be equal to c squared. So c itself would have to be the square root of u squared plus 1. Make sure you do not simplify this by square rooting the u squared and 1 separately. Some students will say that this is equal to u plus 1. That's a big no-no. So this completes our reference triangle, and now we can do step 3. Use the reference triangle to evaluate any of the trig functions at theta. So sine of theta will be opposite over hypotenuse, which will give us 1 over the square root of u squared plus 1. The cosine of theta will give us adjacent over hypotenuse, so u over the square root of u plus 1. The tangent of theta will give us opposite over adjacent, giving us 1 over u. Now for the other 3, cosecant, which is the reciprocal of sine, will give us hypotenuse over opposite. So just rad u squared plus 1 over 1, which I won't write. Secant of theta is the reciprocal of cosine, will give us hypotenuse over adjacent. So radical u squared plus 1 all over u. And then finally, the cotangent of theta is the reciprocal of tangent. It is adjacent divided by opposite, giving us u over 1, or just u, which is no surprise because this is the statement we used to create the triangle in the first place. And we call this a general reference triangle because of the variable u is kept arbitrary. It's not a specified number. Okay, and this concludes our 3rd lesson in the 3-part series on inverse trigonometry.